Hi, dear students. Good afternoon. Myself, Dr. P. Senthil Kumar, Professor in Department of Mechanical Engineering, B.V. Raju, Institute of Technology, Nasapur. Today, I am going to discuss about the topic gears. In gears, various classification of gears and design procedure of spur gear. In this session, I am going to discuss. The remaining part we will see in the another session. So, classification of gears. Gears having different classification based on the arrangement of the shaft. For example, parallel shaft, intersecting shaft, third category, non-parallel and non-intersecting shafts. If you take the first category, parallel shaft, spur gear, helical gear will comes under parallel shaft because the gear will be parallel to the axis of the shaft. The second one, intersecting shaft, is a bevel gear. It is a right angle placement of the shaft. So that is why we are calling it is a intersecting shaft. The third category is non-parallel, non-intersecting. So that arrangement is called worm gears. Worm and worm wheel also we can say. So comes under the parallel shaft, spur gear, helical gear. Helical gear having one more subdivision, that single helical gear, double helical gear. Single helical gear in the sense a single gear only will be placed on the shaft. Double helical gear or another name is herringbone gear in the sense two helical gears will be attached together to produce or transmit more power. That purpose we are using double helical gear. So the second category, intersecting shaft, as I said, bevel gear is the major one, even though we have multiple subdivisions like coniflex bevel gear, zeroed bevel gear, spiral bevel gear, mitre bevel gear, and angular bevel gear, and finally crown gear. Okay, so we mainly focusing the design procedure for bevel gear. The third one, non-intersecting and non-parallel type of shafts and gears. First one, crossed helical gear, hypoid gear, worm gear. Here also the worm gear will be taken for designing the gear. So this classification based on the position of the shaft. So now one by one we will see the types of gear under the classification. First one, I am taking the parallel shaft. As I said, spur and helical gear will be comes under parallel shaft. So you can see the left side here, spur gear. The teeth cut on the profile of the gear is straight teeth. Also, the teeth profile is parallel to the axis of the shaft. The shaft will be placed in the inside the gear. Okay, so this is about spur gear. Coming to helical gear, you can see the teeth are inclined. So some angle will be provided to make a teeth on helical gear. That type of angle is called helix angle. Okay, so this is the second gear under parallel shaft. You can see the image of spur gear as well as helical gear. The teeth are straight in spur gear. The teeth are inclined in helical gear. The second category under helical gear is herringbone gear or double helical gear. As I said, you can see the arrangement. Two helical gears are made together and transmit the power when we require more power to transmit than single helical gear. Okay, so at the same time you can see the faces of the teeth are opposite together merged. Yes, fine. Third category is rack and pinion. So rack and pinion is another type of spur gear. One rack will be cut straight teeth. Another one is spur gear. It is rolling over the rack. So we have three different parallel shaft gears. Okay, spur gear, helical gear, rack and pinion. Coming to the second category, intersecting shaft. That means right angles, intersecting shafts. Bevel gear is a major type of gear. You can see that figure is arranged in a right angle position. Particularly bevel gear we are using in the automobile differential. Differential in the sense it will be placed in the rear wheel of the automobile. So when the vehicle want to make a turn, either left turn or right turn, the steering gear mechanism through the arrangement of propeller shaft, everything will go finally to the differential. Inside the differential, bevel gear will be there. So based on the turn of the steering wheel, the bevel gear will make turn on the wheels either left or right. Okay, so that purpose we are mainly using bevel gears. Another one intersecting shaft, many intersecting shaft we seen under the classification. So here I would like to show one example. Another one example is a zero bevel gear. Yeah. Third category, non-parallel, non-intersecting type of gears. Worm gear is the major role playing in this. You can see the image. It will have one is worm, another one is worm wheel. The worm in the sense it is a straight bar, a threaded portions will be cutted on that. Another one is normal gear wheel. Okay, teeth will be there. Both will be merged together to transmit the power. Main advantage of the worm gear is the speed reduction ratio is 100:1. So we cannot get this speed reduction from the other gears. This is a major advantage, but some drawbacks is there. Mainly, worm gears are made up of bronze, phosphor, this kind of material. These are all very costly material. That is the reason fabrication of worm gear is very costly. Second thing, in the drawback side, we can use maximum transmitting 100 kilowatt only. But in the other cases like spur gear and helical gear, bevel gear, we can go more than 100 kilowatt power to transmit. That is the second drawback of the worm gear. So under the classification, second category is according to the velocity of the gears. So first one, the position of the gear, that arrangement of the gear we discussed. Three category we discussed on that. One is parallel, intersecting, non-parallel, non-intersecting. Spur, helical gears comes under parallel. Bevel and many type of other gears are comes under intersecting. Worm gear comes under non-parallel, non-intersecting. Okay. Now the second classification is according to the velocity of the gears. Velocity in the sense nothing but speed. The speed, based on the speed, the gears will be categorized. One is low velocity gears, medium velocity and high velocity. These three have the range of velocity. Within this range to this is low, second medium and high. Like that we have the categorized the gears. Here I can able to show you the low velocity type of gear in the sense up to 3 meter per second. 1 to 3 meter per second is called low velocity gears. 3 to 15 medium velocity gears. If the speed or velocity is more than 15 is called high velocity gears. Okay, so this is the second category according to the velocity of the gears. Three types: low, medium, high. Low in the sense up to 3 meters, medium 3 to 15 meter per second, and third one high velocity gears means more than 15 meter per second. Third classification according to the type of gearing, how the gear is look like. For example, first one, external gearing. The teeth are cut. In the image you can see the teeth are cut away outside of the profile. Then we are calling it a external gear. The second is internal gearing. You can see here the teeth are made inside the profile. Okay, inside the circumference of the gear profile. So we are calling it is a internal gearing. The third type is rack and pinion. Okay, so this arrangement is totally combination. So both, one is having external gearing, one is having internal gearing, but this combination is providing us a third category. Okay, so this is according to the type of gearing: external, internal, rack and pinion. So next, according to type of gears, gears can be classified as external gear, internal gear, and rack and pinion. The images we seen in the previous slide. So external gears mesh externally. Okay, so it means two gears should have external teeth, then only it can mesh externally, then it will transmit the power. In this arrangement, one may be bigger, another one is smaller. So bigger one will be called as gear, smaller one will be called pinion. Okay, most of the time the design procedure will be go for the weaker one, weaker always pinion when the gear and pinion material is same. If it is not same, we have to identify which one is weaker. For the weaker portion, we have to do the design procedure that we will see in the design procedure topic. Okay, so second one is the internal gear. Here the name will be different. The larger one will be called annular. The smaller one will be called pinion. Okay, so here you can see external gear, bigger one we are calling it's a gear, smaller pinion. When come to internal gears, larger one is annular gear, smaller one is pinion. Okay, so third condition, third type of gearing is rack and pinion. Here the rotary motion will be converted into linear motion. So the rotary motion of the gear will be tend to move the rack into to and fro, left to right or top to bottom. That kind of arrangement is depends on requirement will be there. So the rotary motion will move the rack into linear motion. Okay, as I said, combination of external and internal gears will be there in the arrangement that is called rack and pinion. So very important topic is nomenclature of spur gear, because once you are dealing with the gear, you should know each and every part and what is the name of the part, purpose of the. Okay, so I am going to talk some important parameters in the nomenclature of the spur gear. You can see, first I will take addendum. The radial distance between the center of the teeth to the height top of the teeth, that is called radial distance. I am using the word, not a distance. Radial distance between top of the teeth to the middle of the teeth is called addendum. Same way, if you come to the radial distance between middle to bottom of the teeth is called dedendum. Okay, it's clear? Addendum and dedendum is very important terminology in gears. Next one is pitch line. Actually, you can see the pitch line here. We are calling it is a imaginary line. Okay, you cannot get any visual of that. That is why we are saying it's an imaginary line, but it is used to identify the center of the teeth. From the distance to the top and from the distance to the bottom, we are identifying addendum and dedendum. Next, the gap between the first teeth to the second teeth is called width of the gears. Another parameter you can see is a face width. Face width B, we are calling B, face width. And face and blank. This portion is face of the teeth and this portion is blank of the teeth. And tooth thickness is between the pitch line point of one end to the another end is called tooth thickness. So these are all the very, very important terminologies when you are dealing with spur gears. Okay, so many more are there. We can discuss in the future classes. Generally, the gear materials, as I mentioned here, all are metals. But the gears are manufactured using non-metals also. First, we will see the metals. What are the materials we are using? Aluminium we are using for fabricating the gears or producing the gears. Brass, magnesium, steel. Okay, so these are all the majorly used metals under material category. Coming back to non-metals, we can see wood, rubber, plastic. These kind of gears also produced to work or use in watches, toys. Okay, so metal, non-metal, both category we have the gears. First one is aluminum gear. You can see the image is made up of aluminum. The major property is lightweight. Aluminum is a lightweight material, non-corrosive material, excellent machinability. So these are all the positive points of the aluminum gears. Also, where we are using these aluminum gears, the extremely light duty instrument gears, special lightweight strength application, and where we require high production, low quality commercially. Okay, so these are the applications of the aluminum gear. Coming to brass gear, it is also lightweight, non-corrosive, excellent machinability, low cost commercial equipment only we are using brass gear. Okay, but aluminum gear have lot of applications in a world, having lot of applications everywhere we are using aluminum. Okay, aluminum and aluminum composite, metal matrix composites are replacing many places. Example, in aeronautical application also, previously magnesium was used. Due to the inflammable characteristics of the magnesium, aluminum MMCs are replaced there. Now aluminum is taking major role in aeronautical applications. The third type is steel gears. It having good machining and heat treatable. Heat treatable means you may have idea that when you are fabricating a part through casting, we will get some casting defects like blowholes, right? Blowholes, how it is forming based on the gas retained on the cast part, blowholes will be there. When you are trying to use that particular part for some application, it may fail because of the blowholes. So to avoid that, we used to go for heat treatment of the material, like ironing, anodizing, all the type of heat treatment you might be studied. So for heat treatable characteristics, steel gears are good. Medium ratings and power gears we are using as application of steel gears. Coming to cast iron, low cost, good machining, high internal damping. Application wise, large size, moderate power rating, commercial gears. Okay, so now I done the introduction part of types of gears and materials of gears. The types in the sense classification based on the position, based on the velocity, based on the teeth arrangement, internal, external, like that. So all those things we discussed. Now the last topic of today's session, design procedure of spur gear. So in future sessions, I will start some solving problems in spur gear. Then we will move to the design procedure of helical gear, bevel gear and worm gear. So the further coming sessions we will see one by one. So today the last topic is design procedure of spur gear. Okay, the first step, we have to calculate the tangential tooth load. That is, symbol we mentioned here is a WT is equal to P by V into CS. P is nothing but power. What power rating we are using? V is velocity. CS is service factor. The service factor, it depends upon the number of hours working the gears on the field. For example, if it is working up to 8 hours in a day, the CS may be taken as 1. if it is 8 to 16 hours, 16 to 24 hours, the classification we have in a table in our design data book. Particularly any kind of design data book you are allowed to use in examination, but you should identify which part or which page it is available. That is your role to prepare for examination. If you find the table based on the question given in the related to timings of the gear, 8 to 16 hours, it may be 1.5. 16 to 24 hours, it may be 1.75. So you have to pick up from the table and substitute here, find the tangential tooth load. Okay, so velocity formula we all know that pi d n by 60. Okay, so this is the first step. Then, so as I said, the type of service CS is shown in the table. You can see there they mentioned intermittent or 3 hours per day, 8 to 10 hours per day, continuous 24 hours per day. So based on that type of load given in the question, you have to choose either a light shock, medium shock, or heavy shock. For that, this particular 8 to 10 hours means 1.25. Like that, the CS has to take. Okay, fine. So once the first step, WT, tangential tooth load, is completed, next we can start working applying the Lewis equation. By using the Lewis equation, once again we are going to calculate WT. Here another one formula we are using. So here sigma B pi my, nothing but sigma stress, B phase width, M module, Y form factor. Okay, by substituting all those value, you will get another WT. So at the end of second step, we will have 2 WT, that is 2 tangential tooth load. By comparing that, the unknown value module may be calculated. I will show in the next slide. So as I told, you will get 2 WT. One with power, it have the value. Comparing with the second Lewis WT, it consists of this module. Comparing both the value at the end after the simplification, module M may be calculated. Okay, that is the third step. The fourth one, the product of sigma and Y form factor, stress and form factor should be calculated. Why? In the sense, in the starting about material I mentioned, the question given both gear and pinion as same material, you can take pinion as weaker. If material are given as different for gear and pinion, you have to calculate this product of sigma and Y. This result will give you which one is less value. That value may be pinion or gear. You have to design further for that. Okay. Okay. The fifth step, once you calculated the module, you can use that value for finding phase with B. Then we have to calculate dynamic load WD. Okay. WD formula is WT plus WI. The WI, we have another formula 21VBC plus WT by 21V plus square root of BC plus WT. The WT already we calculated, we have the value. B just now phase width we calculated. Velocity we have, only the C value we have to calculate. That formula also available in the design data book. You have to take the value, take the formula and find out, substitute, finally you will get WD. Okay, WD in the sense dynamic load. Okay, so the next step, the beam strength WS we have to calculate. That formula is available in the data book. The required page number I am not mentioning here because the different data book having different page numbers. That is the reason I didn't include any page number here. Okay, so after that, finally you have to calculate the wear load, wear tooth load. So first we calculated tangential tooth load, second we calculated dynamic tooth load, third we calculated beam strength WS, Finally, we are calculating wear tooth load W. The only important point is you compare all the loads in the problem, the WV should be greater than other loads. Then your procedure is correct. Wherever you assumed some values, wherever you calculated the values, all are correct. If in the sense WW value is less of any one of the other load value, we have to change the procedure from the starting itself. We have to consider the higher end values. Then finally you will get safer value. So then you can say your design is safe. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.